Greetings from the Department of ECE, SJBIT. In this session, we are going to learn about losses of losses of a two-port network in a microwave system and the properties of S parameters. So in the previous session, as we have learnt about the scattering parameters, which is a representation for a two-port or multi-port network. Then followed by we had seen about representation for a multi-port network also, S parameters for a multi-port network also. And in this session, we will look into the losses in a microwave network, followed by the properties of S matrix. So first, if you look into the losses in a microwave network, if you observe in any microwave device or a circuit, we have several losses which can be expressed in terms of S parameters when the ports are match terminated. Suppose let us consider we have a two-port network. So in that two-port network, we had given an input from port 1. Let us consider that power as Pi, and some of the power will get reflected back at the same input port. We represent that as PR, which is reflections mainly due to impedance mismatch. Then some of the power will enter into the load. We consider load has been connected at port 2, and the power which is going to port 2 considered as P0. If we consider such system, then we can express the S parameter, we can express the different types of losses like insertion loss, reflection loss, return loss and transmission loss. All these values are expressed in decibels and they are expressed in S parameters also. Suppose coming to the first loss, we call it as an insertion loss. It is nothing but a ratio of input power to output power. Suppose let us consider I had given a 10 watts of power, input power, and only 6 watts of power which has been reached to the output. Pi to P0 ratio, that is 10 divided by 6, will give you the insertion loss, the amount of insertion which has occurred in the device, in the network. Okay, so if as I am expressing this in decibels, so you need to take a 10 log. If it is a voltage, then it is 20 log. So 10 log Pi by P0. In a two-port network, we know that incoming wave can be represented in terms of power. The incoming wave function, input power can be represented in terms of incoming wave function as half into A1 square, and half into A1 square divided by P0. P0 is the power delivered to the load. So same two-port network, if you observe, B2 is the one which is outgoing at port 2. So that power which will be that wave function which will appear as power output in the load. So B2 half into B2 square gives you P0. So you half will get cancelled, left out with 10 log A1 by B2. So you divide the numerator and denominator by A1, gives you numerator as 1 and denominator as B2 by A1. So B2 by A1 is nothing but S21. Already we know that B to A ratio is nothing but S value. B to A is nothing but S value. BI by AJ representation. So you got a 20 log square, we have no whole square. If you convert, then you'll get 20 log of 1 by S21. Or you can also, if the device is symmetrical, then you can say that it is equivalent to 20 log 1 by S12. So insertion loss, which is nothing but a ratio of input power to the output power, not output to input. Output to input will give you the gain. Input to output ratio will give you the loss. Similarly, another type of loss which we have is a transmission loss, or we call it as a attenuation. At the input port side, if you observe, input power is Pi and reflected power is PR. So Pi minus PR is the one actual power which is entering into the port. Suppose let us consider 3 watts has been reflected, and P0 as 6 watts and Pi as 10 watts. So which gives you, this is transmission loss, gives you the ratio of actual power which has been fed to port 1. So which is nothing but Pi minus PR. So 10 minus 3, 7 watts divided by the power output. Power output we got 6 watts. So that means remaining 1 watt which has been during the transmission from port 1 to port 2, it has been lost. So that if we are accounting, so that is nothing but a transmission loss. 6 by, sorry, 7 by 6. The same thing you can also express in terms of S parameters as Pi is half A1 square and PR is half B1 square. So A1 half you take common, even denominator half B2 square, half will get cancelled. So we'll have A1 square minus B1 square. A1 square you take common in the numerator, gives you 1 minus B1 by A1. B1 by A1 is nothing but a S11. 1 minus S11 square in the numerator. In the denominator it would be B2 by A1. So B2 by A1 or B1 by A2, S21 or S12 square. That is about the transmission loss. Coming to reflection loss, it is nothing but the ratio of Pi to Pi minus PR. That means actual power which you are generated from the source end and actual power which has entered to the into the port 1 or into your microwave component. So Pi, suppose if I consider 10 watts and PR is 3 watts, Pi minus PR, so gives you 7 watts. So that means 10 watts if it is generated, actually it is entering only 7 watts. So the remaining 3 watts got reflected. So 10 by 7 gives you the reflection, the amount of reflection. Even this you can express in terms of S1, S parameters, considering Pi is A1 square, PR is B1 square. A1 square divided by A1 square minus B1 square. A1 square you take common. So 1 divided by 1 minus B1 by A1, which is nothing but S11 square. So same manner you can express the other losses, which is a last one, which is a return loss. Even this is expressed in terms of decibels, and it is defined as a ratio of incident power to the reflected power ratio. Incident power to the reflected power ratio. 10 watts I had given, reflected power we got as a 3 watts, 10 by 3. So gives you the return loss. Or you can express this in terms of power, no, you can express in terms of A1 square divided by B1 square. Right. So 20 log A1 by B1. A1 by B1, again A1 you take divide numerator and denominator. So 1 divided by B1 by A1. B1 by A1 is nothing but S11. So 20 log S11. S11 is nothing but the reflection coefficient K at port 1. So K1. So this is about the different types of losses usually which occurs in a two-port network or in a microwave device or microwave network. Then coming to the properties of S matrix, next topic. So properties, first property, if you observe S matrix, it is always a square matrix and it is of order n cross n. N indicating the number of ports, how many ports that you have. If n is 2, then you have a 2 cross 2. If n is 10, 10 cross 10, likewise. So and all these S parameters are complex quantities. Complex quantity indicating it has both real part and imaginary part. You have attenuation as well as a phase variation. Now in the second property, if you look into, which is a phase shift property of S matrix. Suppose if I change the reference plane in two-port network from 1 to 1 dash or 2 to 2 dash, the variation of S parameters which is accounted with only phase. So at the input side and at our output side we are changing the reference plane. Here you can observe 1 dash reference plane is changed. Here 2 to 2 dash it has been changed. So when you change the reference plane, you will have a variation in phase. So that is accounted over here, e power minus j51 and e power minus j52 at S11 and S12 values. Not it has an effect on at port 1 and port 2. So similarly, multiplied with the S matrix of the device, and again you multiply with the phase change which has occurred at port 2 due to change in reference plane. So e power minus j51, e power minus j52 along the diagonal components. So if you look at the final S matrix, You can observe when you change the reference plane, attenuation is not happening, only the phase is varying, phase is changing. So that is accounted here. Okay, e power minus s11 and to e power minus j5 251, and here you have e power s12 into e power j51 plus phi 2 phi 1 plus phi 2, same phase shift property. This shows phase shift property. Similarly, the other one, uh, third property of S matrix is the diagonal elements becomes 0 for a perfectly matched network. Meaning, suppose if you have a n port network, so assume that all the ports are match terminated. So if all the ports are match terminated, then their corresponding reflection coefficient, so that means S11, S22, S33, indicating the reflection coefficient at port 1, port 2, port 3 and so on. All these values will become 0 under perfectly matched conditions. So you can say that all the diagonal elements, if they are becoming 0, meaning uh, the n-port network is perfectly matched. It has been terminated with a perfectly matched termination. So coming to the next one, S matrix, another property, S matrix is symmetric for a reciprocal network. Symmetry property indicating that Sij is same as Sji. That means in either direction, reciprocal network or reciprocal device, if you consider, it has the same transmission characteristics in either direction. Means pair ports you can interchange. Meaning is this: ports you can interchange. Even if you interchange the ports, you won't have a variation. uh, and you can observe it can be represented, or you can cross verify the symmetry property as, if you have S12 same as S21 or S31 same as S13, are indicating that Sij which is same as Sji, where condition I not equals to j. So I equals to j case becomes diagonal component. If I not equals to j, then if it is satisfying Sij same as Sji, you can say that the S matrix is symmetric. And or you can also cross verify by considering a transpose of the S matrix. So take a transpose of the given S matrix. If the transpose is same as the S matrix, it says the device is reciprocal. Okay, so that is about the fourth property. And the last property, important one, which is S matrix, it has a unit, it satisfies unitary property for a lossless network. Suppose if the network is lossless, then it has to satisfy the unitary property. According to unitary property, it says S conjugate transpose multiplied with S must be equals to identity. S conjugate transpose multiplied with S must result in identity. So you can cross verify the same identity unitary matrix by using any of these two any of these two conditions. So first condition says when I equals to j, when I equals to j case, which I am considering, when I equals to j case, if you consider the sum of the products of every term or each term of any row or any column of the S matrix, if it is multiplied by its conjugate, complex conjugate, which must result in unity. So according to this, the S11 multiplied with complex conjugate S11 multiplied with S11 square, so the conjugate, plus S12 multiplied with S12 conjugate, and similarly S13 multiplied with S13 conjugate must be equals to 1. Or you can say that S1 row or column, any row or any column, if you consider, if you take a complex conjugate multiplied with the S value, obviously you will get a square of that. So first row, if I consider S11 square plus S12 square plus S13 square must be equals to 1. And similarly, if you consider the other, similarly for the column also it satisfies all the rows or all the columns, it will be satisfied. In the another condition is you need if you the sum of the product of each term of any row or any column of an S matrix multiplied by the complex conjugate of a different row or different column, then the result must become 0. So it indicates that the columns are orthogonal to each other. So considering the row wise, if I say S11 multiplied with S12 conjugate plus S11 multiplied with S13 conjugate and so on, which must result in 0. So you can prove this unitary property. We will discuss that proof in the next class, next session. Now let us consider they have given a problem stating that you need to identify that given an S matrix and you have been asked to determine whether it is reciprocal or lossless. So for first condition to cross verify whether it is lossless or reciprocal or not. So verify S12, S21. Both are different now. Even though magnitude same, but phase shift you have minus 45 and plus 45. So this says as S12 is not equals to S21, you can directly say that this matrix is not a reciprocal or it is not symmetric. Same way, in this case if I want to verify 0.9 at a 90, 0.9 at an angle of 90, both are same, you can say that it is reciprocal. And in this case S12 same as S21, even in this case both are same, you can say that all the devices are reciprocal. For checking lossless, unitary property to be cross verified. We will take up a problem along with unitary property proof in the next session. So what we have seen, I'll just revise. We had seen B can be expressed in terms of A. B is equal to S into A for a port network. B1 by A1 ratio, which is nothing but S11. We also call it as a reflection coefficient at that particular port. So A is nothing but incoming wave and B is nothing going wave, normalized one. And you can express B is equal to S into A. You can also express that in terms of S matrix. And you can calculate from this S11, S12, S21 and S22 by taking a ratio of B1 to A1, B1 to A2, B2 to A1 and B2 to A2. Considering the other ports as a match termination. We call that as input reflection coefficient, output reflection coefficient. Middle to S1 to S21 are transmission coefficient. It may be forward or reverse. And similarly, we say that Sij is nothing but a ratio of B to A. So B is outgoing and A is incoming. And Ij, you observe Bi to Aj ratio, not Bj to Ai, Bi to Aj ratio. And concluding that all other ports, other terminals or other ports must be terminated. And reciprocal property, as we had seen, Sij must be equals to Sji. Condition I not equals to J. Then if it satisfies, you can say that this network is symmetric. And reciprocal you can also cross verify with the transpose also. And for lossless, unitary property has to be satisfied. S conjugate transpose multiplied with S must be equals to unitary. Or you can say that the same thing. You need to either row wise or column wise. If you take a sum of the product of the particular element in any row or column multiplied with the complex conjugate of it, which must result to unity. And similarly zero category also, if there means any row, the sum of a product of any row or column of an each element with its adjacent row element conjugate must result in unity 0. And that's what here you can cross verify. You observe, so 1 has to become S11 square plus S12 square plus S13 square must be equals to unity, or S11 square S21 square plus S31 square must be equals to unity. Or you can say that row, all three rows S121 S22 S23 square must be equals to 1. So S13 S23 S33 must be equals to 1, first one. Orthogonality concept you can cross verify by considering any row multiplied with its complex conjugate of the next column, next row. So take a sum of that, which must result in 0. So S12 S11 into S11 conjugate plus S21 into S22 conjugate plus S31 into S32 conjugate, which must be equals to 0. Same way, first column and third column you can cross verify. S11 13, 21 23 conjugate, 31 33 conjugate, which must be 0. Similarly, column 2 column 3, 1 2 1 3 is conjugate. And similarly, this we have verified with respect to the columns. Same way you can cross verify with respect to the rows also. If a network satisfies this, then you can say that it is logical. Similarly, you can cross verify for Z matrix and Y matrix. They'll become symmetric if and only if Zij equals to Zji and Yij equals to Yji. If a network satisfies this condition, then condition is I not equals to J. If a network satisfies this condition, then you can say that it is symmetric. Okay, in the today's session we had seen the properties of S matrix, then losses associated with a in a microwave network, like insertion loss, transmission loss, transmission loss or attenuation, then reflection loss and return loss. Then followed by the properties, 5 properties. Diagonal, all diagonal elements must become 0 for a matched network, and symmetry property, Sij equals to Sji. Then unitary property, S conjugate transpose multiplied with S must be equals to identity. Then we had seen a phase shift property. If you change the reference plane, the phase of that will be accounted. Then we had seen S matrix is a square matrix of order n cross n, and S is a and it is real, means it is a complex quantity. You have a real, both real and imaginary parts. Thank you. We'll stop.